The first one is Boyle's law. Boyle's law states that pressure is inversely proportional to volume, temperature, and the number of moles constant. So if you know that if you put pressure and volume on one side, you get K, which is some constant. So if you're comparing just pressures and volumes, you get P1 V1 is equal to P2 V2. Now I'm going to go over here and show you how you would do this using the ideal gas law. When you do this, you put everything that's changing on one side. These are all constants. So you end up with PV equals your constant. So that means P1 V1 is equal to P2 V2. And the reason this works is if you remember your laws of mathematics and proofs, if A is equal to B and B is equal to C, then A is equal to C. And because your constant is the same each time, then you can compare them. Now, if you apply Boyle's law, what you'll see is volume versus pressure. As volume drops, pressure is going to increase. Or if you look at them as V versus 1 over P, then they're straight. It's a straight line. Okay, so they're proportional. Now, what are the practical effects of pressure? Well, one of the things, and this is from a different text of Pearson, is if you've ever been swimming in a swimming pool and you play the game where somebody throws something down and you have to go get it, when you go to the bottom of the pool, what you're doing is you feel much more pressure because you get the atmosphere plus the column of water here. Whereas if you're at the top of the surface, you only see the atmospheric pressure. So this is why if you dive, you have to worry about pressure effects. Okay, more about that in a minute too. So Charles's law was volume is proportional to temperature. Pressure and moles are constant here. Now, here's the trick. Temperature must be in Kelvin. Wait a minute. Why? Why does temperature have to be in Kelvin? Well, think about it. On the Celsius scale, your temperature can go negative. Okay, same thing with the Fahrenheit. Well, you're thinking, well, you can't. That's okay. Well, if temperature is negative, then volume is negative. Well, wait a minute. You can't have negative volumes. Think about it. How do you measure a negative cup? Can't do that. So Kelvin is the only scale where all the values are positive. You start at 0 and you go up. So that being the case, all the temperature has to be in Kelvin. Okay. So if you look at it, volume is equal to some constant K, like we saw before. Remember, this is your constant, is equal to T. So V1 over T1 is equal to V2 over T2, or T1, T2. Okay, these drive me insane. So I'm going back to my PV equals nRT, which is my ideal gas law, which we'll get to. And you circle what is changing. So you put them all on the same side. So that means nR over P. This becomes your constant. So that means V1 over T1 is equal to V2 over T2. Now, here's the thing. A lot of people memorize Boyle's law and Charles's law. If I need you to use Boyle's law, I'm going to tell you Boyle's law states that pressure is inversely proportional, is inversely proportional to volume. Or Charles's law, where volume is directly proportional to temperature. I'm not going to say, remember, what is Charles's law? I don't remember what Charles's law is. So if you need exactly that law, then I will give you the value. So don't sweat small stuff on there. But what we're looking at is how things vary. Okay, so let's talk a little bit more about the absolute temperature. We've actually gone through this. Remember, K is 273.15 plus whatever degree C you have. So make sure you're always there, because absolute zero is a negative 273.15. Now remember, I am not giving you this. I've told you this before, and you're expected to know that particular conversion. Okay? So here again, if we look at the effect on a balloon of a sunny day or heat versus cold, in sun it gets bigger, in cold it gets weaker because it's smaller, because volume is directly proportional to temperature, increased volume, decreased temperature, decreased volume. And there we go. The practical effect of Charles's law, and I'm not going to lie, I really like this one because the little fish has fangs. Okay? But the other thing is this. Remember, Charles's law states that, I can't even remember, is volume is proportional to temperature. So what happens is that if you go down in the water, two things happen. You get a greater pressure and the temperature drops. So it has really weird effects on both a balloon and, more importantly, your lungs. And so the practical effect of Charles's law is that you can't have an inordinately long snorkel. So while this is true, like in Fred Flintstone, this is not. You cannot do this. You can't breathe from a snorkel that's too long. Okay, that brings us to the next law, which is Gay-Lussac's law. And he says that pressure, again, is proportional to temperature, volume, and moles are constant. So if you're noticing PV equals nRT, if you're looking at 2, the other 2 have to be held constant. R, you're going to find out, is the gas constant, so it ends in constant. So it is a constant. So here, pressure over temperature is equal to K. So P1 over T1 is equal to P2 over V2. Again, temperature must be in Kelvin. And the absolute zero is, because absolute zero is K. And remember, if temperature goes negative, then your pressure goes negative, which doesn't work. Okay. Now, Gay-Lussac's law, I always like to share trivia so that you see that there are practical applications. In 1804, and we're in 2020, so if you think about it, this is only 200 years ago. The big thing was everybody was playing with hot air balloons because they were trying to move around better, etc. Well, we talk about extreme sports now where people are jumping off of cliffs with a suit that has bat wings. Okay, no, I'm not doing that either. But the first extreme sports people were scientists in England, because what they did was they would go up in the balloons. Well, Gay-Lussac's friend was Jean-Baptiste Biot, which when you get to organic, you'll encounter Biot. But the point being is that they would go up in these balloons and they would have a long rope down below, so that as they went up slowly, if they, when you get too high, they would literally pass out because of lack of oxygen. So at that point in time, there would be no activity, and so their friends, assuming they had friends, would pull them back down, and once they got lower down, then they got enough oxygen in their lungs, they would stop passing out. So what they would literally do was go up and take samples of air before they passed out. So bottom line is the first extreme sports dudes were playing with hot air balloons, because you had to rely on your friends to pull you back down. And I don't know about y'all, but some of my friends are a little sketchy, shall we say. Okay, so if we're looking at these things, pressure does what when volume decreases? Well, they're inverses, so pressure is going to increase. When temperature decreases, volume is going to decrease because they're directly proportional. Pressure does what when temperature changes from 24? Well, so the temperature is dropping, so the pressure is going to drop or decrease. Here, the temperature is increasing, so the volume will increase. So always keep in the back of your mind what's going on so that we can see whether we have a reasonable answer or not. Okay, another law, Avogadro's law. Avogadro of your 6.022 times 10 to the 23rd particles Well, guess what? He was playing with gases too. And he determined that volume was proportional to N if pressure and temperature are constant. And so what that means is equal volumes of different gases contain the same number of particles. Okay, this actually makes life a whole lot easier for some things. So at STP, the volume of 1 mole of gas is 22.4 liters. This is called the molar volume. And you probably want to know this because it is not, while it's constant, it's not one I give you. Now, we used STP. What's that mean? STP is standard temperature and pressure for gases. It's 1 atmosphere and 0 degrees C or 273.15. You need to know that because later in chapter 5, we're going to talk about STP conditions for thermodynamics, which are different. So the trick is if you notice that at standard temperature and pressure, doesn't matter what our gas is, our volume is the same. And they all contain 1 mole of particles. Okay? So that's Avogadro's law. So now let's work some of these individual gas laws. Okay, so if a gas sample occupies a volume, so we're going to call this V1, and a temperature, this is T1, and I'm not going to lie, I immediately start converting temperatures. So T1 is 302.35 K. What volume will it occupy? This is going to be T2, which is going to be 358.85 K. And wait a minute, what volume? So V2 is your unknown. So PV equals nRT. So that means V1 over T1 is going to be equal to V2 over T2. Now this is where the A word comes into play, you know, algebra. And I like to rearrange. So I'm going to say I want V2. V2 is going to be equal to V1 over T1 times T2. Okay? And then I like to plug in. But some of y'all like to cross multiply, plug in, whatever. Whatever floats your boat. The rule is as long as you obey the rules of mathematics, you're fine. If you do not obey the rules of mathematics, then, okay, you're in trouble. Okay, so if you need to go back and review your algebra, then you can. So V1 is 348 milliliters. T1 is 302.35 K. And T2 is 358. Oh, wait, I just reversed those because I need T2 on top. See, reading is fundamental. And if we don't read, we get in trouble. So I need T2 on top, which is 358.85 K. And I need T1, which is 302.35 K. So if you think about it, temperature and volume are proportional. So the temperature is going to rise, so your volume should get bigger. Okay, so when we do the math, we end up with 413.03 milliliters. Okay, now, significant figure-wise, this gets a little ugly when we're dealing with the temperature conversion and then whatever. So in the gas laws, and especially doing these quizzes on D2L, I'm going to tend to sometimes, especially in this chapter, specify significant figures. Now in chapter 5, we'll go back to, you can tell them easier. So I don't usually, but in the gas laws, I'll usually give you significant figures. So if I told you 3 significant figures, it'd be 413. Now here's the next question. Wait a minute, this is in milliliters. Can I leave it in milliliters? Yep. The only thing you cannot leave alone is temperature. As long as your volumes are both milliliters, you're fine. You can convert from milliliters to liters. I could have asked for this volume in liters. If I did that volume in liters, then you would give me 0.413. If I don't specify, you can give me in milliliters. Being D2L in quizzes are a little annoying. I will specify only because you've experienced that twice now. So the bottom line is we just work the problems and set it up. Okay, did I just skip one? Yes. Carbon monoxide burns in oxygen to form carbon dioxide. The volume occupied at 38.5 milliliters. Okay, in 1 atmosphere, what volume of oxygen at the same temperature and pressure? Okay, so if the same temperature and pressure, then we're not changing. Okay, we're doing a reaction. So reactions means moles in the equation. Okay, so wait a minute. Avogadro's law says that volume is going to be proportional to moles at the same temperature and pressure. So if we're looking at this, you got the volume, you have 298 milliliters of CO. And what you're looking for is the volume of O2. So if we look at our equation, we have 1 mole, no, we have 2 moles of CO for every 1 mole of oxygen. So your moles cancel and your CO cancels, so you end up with 149 milliliters of oxygen needed. So in this particular case, I didn't need to convert the temperature because I wasn't using it. And I don't have to worry about the pressure, even though it's given, because again, wasn't using it. All right. Suppose you have a gas sample that occupies 727 milliliters at atmosphere and okay, so our volume at 727 milliliters. Our pressure is 2.86 atmospheres. And our temperature is 34.9, which I can write down. But I immediately want to convert that to Kelvin. Here's the thing. If you convert it every time, even if it takes a little extra like on the previous problem and you don't use it, big fat deal. But if you forget to convert it, it will get you in trouble. So wait a minute. Which will this gas occupy? The conditions are changed to 158 milliliters. And temperature is 14.2 degrees C, which means it's 287.35 K. And we're looking for pressure. So wait a minute. What are we doing? So PV equals nRT. So what's changing are these three. So PV over T will be a constant in R. So that means that if it's 1, then P2V2 over T2 will be the same. So again, that will drop out. So this would be 1, 1, 1, 2, 2, 2. Now the trick is keep your 1s and your 2s together. And again, I'm annoying. So I would take P1 V1 over T1. So my T2 would go to the top and my V2 would go on the bottom because, remember, if I'm moving to the other side, I do the opposite. So if it's in the numerator, I have to divide it. If it's in the denominator, I have to multiply it. So then we get P1, 2.86 atmospheres. V1, 727 milliliters. Over T2, which is 287.35 K. Divided by T1, which is 308.05 K, and V2, which is 158. So you kind of have to keep your species together. P2 comes out equal to 12.2753 atmospheres. Again, if I needed it in 4 significant figures, you would report it as 12.28 atmospheres. Okay, so these are really not difficult as long as you A, obey the rules of algebra, and B, read. And I'm not going to lie, I'm as bad as everybody else at occasionally not reading. Okay, so a 75 milliliter sample of gas exerts a pressure of 550 torr at 35 degrees C. How many milliliters will it occupy at STP? Okay, so V1 is 75.0 milliliters. P1 is 55.54 torr. Okay, more about it in just a second. T1 is 35 degrees C, which we want to convert 308.15 K. So now wait a minute. Again, we're P1 V1 over T1 is equal to P2 V2 over T2 like we did on the previous slide. So then that means I need V2, T2, and P2. Well, how many milliliters? So V2 is our unknown. STP, standard temperature, is 0 degrees C, which means it's 273.15. Okay. Pressure is 1 atmosphere. Okay, so here we either have to convert 554 torr to 1 atmospheres, or this is 760 torr. So it's easier to do that way. But if you do convert the 554 torr to atmospheres, you'll end up with the same answer. It won't matter. So P1 V1 over T1 is equal to P2 T2 over V. See, there I go. Not being able to read again. Okay, V2 over T2. So V2 now is P1 V1 over T1. And to isolate the P2, I'm going to multiply both sides by T2 and divide both sides by P2. So I get 554 torr times 75.0 milliliters. And T2 is 273.15 K divided by T1, which is 308.15 K divided by 760 torr. Okay, now I've been writing in my units. For some bizarre reason, everybody in gas laws thinks, oh, units go away. But if you keep up with your units, so you're like, okay, the K's canceled, the torr's canceled, I'm left with milliliters. So as long as the math works, I should be good. And I get 48.4616, again with the reading, 46 milliliters. Now, if I'd asked for 3 significant figures in liters, then you would report as 0.48 liters. Okay, I will tell you how to report it, and we're good. So, actually, gas laws are really, really easy peasy, as long as you do 2 things. One, you keep up with your units and make sure all your temperatures are converted to Kelvin, and you're canceling milliliters with milliliters or liters with liters, atmospheres with atmospheres, torrs with torr. And you remember your algebra, because the algebra drives people insane, because they're like, oh, I multiply by T1, not T2. No, you got to follow your algebra through. These are the individual gas laws. The next section we'll do are the